talking about real groupoid and what the very motivation of this work is to the classification which is related to the way to the last talk, the classification of difference by K-R theory. So the idea is to develop a twisted version of a TSK-R theory for the general setting of groupoid with evolution. So let me start with some definition. A real groupoid is just a groupoid equipped with an evolution. So maybe I will issue the quality of the groupoid. So just a groupoid is given by a space G1 and G0 for the unit space. G1 consists of morphism and this line G. X is called the source of G, and Y is the range of G. So there is two maps here, which are supposed to be continuous. So we define in an obvious way morphism of real groupoid. It's just a morphism of groupoid that intertwines the involutions. So let me give an example. Like a real space in the sense of it here can be viewed as a real groupoid whose unit space and the space of morphism are identified with the space. So given such space, we can endow K theory with this involution. The variable is the complex conjugate of the bundle, such that the fixed points, the set of fixed points is actually a group which can be identified with the TSK-R theory X. Another example is LPQ with involution XY maps to X minus Y. Well, we can define two categories of real groupoid whose one morphism are called generalized morphism. So let me express this in a picture. Here we have gamma 0, and here G0. Z consists of is a set of arrows from gamma to G with the property that given two arrows with the same from the same source here, Z with Z prime, there is a unique morphism here, G, connecting their type. This is called generalized morphism. And of course here two morphism will be just a morphism one continuous map from Z1 to Z2, which is gamma G equivalent in this order and compatible with all the involutions involved. There is a composition of one morphism defined in this way, and this is just a fiber product of Z1 and Z2 over G1 modulo the equivalence relation that identifies Z1, Z2 with the elements in the right hand side. So now we define this category LG as just a category of real groupoid, and morphism are isomorphism classes of generalized morphism of one morphism. So now if we derive by LG as the category of real groupoid and strict morphism or groupoid morphism, there is an obvious or a natural counter that associate to each strict morphism this generalized morphism. Well, the action here is given by, so the gamma action over ZF is given by gamma S of gamma G is L of gamma F of gamma G, and the G accent is the obvious one, I mean just the left coordinate. So, example of real groupoid, which is Morita equivalent to G, is the so-called polar groupoid. This is given an open cover of the unit space. We can suppose that U is real in this sense. Otherwise, we just put, for example, E is E prime times plus 1 plus or minus 1 with, for instance, U E is E prime minus 1 is tau of U E prime. So this is not a restriction. And GU is, well, the morphism is consists of the triples of the form IGJ. So this is a kind of cocycle, actually, or J cocycle. And we can, it is easy to see that this groupoid is Morita equivalent to G. Well, the aim of this result actually is to work with strict morphisms instead of generalized morphisms. So, I mean, for this end, I introduce the category of open, polar groupoid defined in this way, so which is maybe I could explain the stage of this proof. So I mean there is a result by Hilsum standards and Jean 2 that say that given a generalized morphism from gamma to G, we can always decompose Z in this form, gamma U to G, this is FU, and the injection here, so that Z is actually isomorphic, Z is isomorphic to the decomposition of the induced generalized morphism of FU with Z and U inverse. Well, I will also define some introduce some basic elements which are known for those who are familiar with groupoids, are called Grade S1 groupoid O extensions, which are a generalization of the so-called bundle job of a space. So this is just a line bundle or S1 principal bundle over G and a morphism of groupoid from G to Z with 2. There is a Morita equivalence defined in the collection of such objects such that we get a group, an abelian group called the group of extension over G. Now, an S1 central extension of G is just the data of S1 real-graded S1 groupoid gamma tilde over a real groupoid which is Morita equivalent to G. We define, of course, a Morita equivalence over the collection of central extension induced by the Morita equivalence defined on the S1 regraded S1 groupoid over G, and we get this isomorphism, which is, which comes from the next lemma that identifies the groupoid of real groupoid as generalized morphism with that of real potent groupoid. There is a result of by Fried, Hopkins, and Kellman, Jean-Luc and Laurent that gives this result in the usual case without varying or involution involved. So now let me define this. These objects called the Dix-Melody bundles, or regraded Dix-Melody bundles are just Dix-Melody bundles or sister bundles A, which are at the same time real space, so that the projection is real or compatible with involutions, and an action of G over A. That means that we have a family of graded isomorphism of Caesar algebras as G from the fiber over the source and the fiber over the range, which verify these properties. Induced by the involution over the fiber bundle is actually a conjugate linear, complex conjugate linear isomorphism of graded Caesar algebras, and each fiber is a graded elementary Caesar algebras. While I recall that the elementary Caesar algebras is Caesar algebras isomorphic to the algebra of compact operators over a Hilbert space, while if it is of parity 0, so it is for this form, H is actually a graded Hilbert space, or of parity 1, the form is in the form K of H plus K of H, with the odd gradient in T1, T2, T2 plus 1. And here the gradient is given by the joint of the conjugation of the unit U. And we require that the G action is compatible with the involutions. For example, we can construct a natural such bundle by picking a R system mu and taking H phi is just the separable, the infinite dimensional separable Hilbert space identified by 2 copies, and with the gradient, with the order gradient, and we form K0G in this way. So now we can define morphism between two such bundles, and this way, this is just a bundle of, or a morphism of fiber bundle that respect the star involution of the Caesar algebra, the norm, and of course the grading and also the real structures over the bundle. So we say that two such bundles are Morita equivalent if, after transforming by K0G, they are isomorphic. So this is also known as stable isomorphism in the those who are familiar with Caesar algebras. Now, a twisting of KR of G will be just an equivalence class of real graded bundle over G. So we define sum over this the collection of or in BRG journal by the graded tensor product which is defined pairwise. And the action, or the G action also is defined pairwise, but there are some tricks here to be considered. So the abelian group obtained is called the real-graded Brauer group, which is a kind of generalization of the Brauer group of Wall and Donovan Toby. So the very simple case is when G reduces to a point, and then we find out that its Brauer group is azimuthal to Z mod 8. Well, to see this, well, just to note that a real-graded busy bundle over the point is just a graded elementary super algebras and those with a real structure. But for example, for the parity 0, a real structure is given by a real structure of quaternion structure over the Hilbert space. So we get 4 types of them, depending on the degree of J and also the sign of J square. And of course, we get 4 types for the odd parity also. So, well, to give the homological picture of this group, I will first introduce a group here that I call the group of involutive elementary triples, which are a triple. This time K hat and K hat bar are real-graded. Well, that's not really there. Sorry, are graded elementary scissor algebras of the same quantity, such that K hat bar is isomorphic to the complex conjugate algebra of K hat. T is a complex linear isomorphism, complex conjugate linear isomorphism of graded scissor algebras. So this is not, I mean, there's no natural map from this group to Z mod 8, since K hat may not be a real scissor algebra. So I define this group in this way. I just mod this collection by the stable isomorphism of scissor algebras. Then I get this theorem, which is a kind of generalization of Donovan-Kaobi theorem for the orthogonal Brauer group of the space. The problem is that this group in K is very huge, because it is, I think it's actually isomorphic, well, not isomorphic, but it is the same as given for each graded elementary scissor algebra, a automorphism, an element of K. But hopefully there is some simple case where this group, we don't need this group. For example, the case where tau is trivial, then we find exactly the orthogonal Brauer group. And also, when tau is fixed point free, we find a nice decomposition of the graded Brauer group of G, which is just the group of graded elementary scissor bundle over G. And well, this decomposition is given by the involution defined over G hat by A tau star, so same one as for X. So maybe I will, for the 30 seconds, just show how we find out the second component here, extension. So we can, for example, suppose that A is of the form K of Hx, and then we put for H as this joint union of H at X, and you form the following groupoid U. The projective unitary of U hat, which is the disjoint union of Hx, Hy. This is in fact a groupoid with unit space the same, the unit space of G. And then we get a kind of extension U1, U hat to PU. And so the grading is given by the degree of the projective unitary here. And then we choose a local trivialization of A, so that we and then we take the frame bundle of A, which is normally a PU principal bundle, which is the same thing as giving a generalized morphism from G. The open the covariant groupoid over the trivialization chosen to PU of H or of H hat. And then we just have to pull back this extension over G, then we get a central extension of G.
Thank you very much. Any questions? Well, I guess we're going to say thank you again.